Hello there, and welcome to the Quantum Slumber, a quiet place where science takes the long way home, and your mind gets permission to loosen its grip. Tonight's question sounds ordinary at first, comforting even. Do you trust the world to stay solid? Do you trust the floor to hold you, the sunrise to keep its schedule, your body to remain itself from one second to the next? Most of us do, not because we proved it, because we got used to it. But deep underground, where the air is still and the machines are patient, physicists have built instruments that can hear the universe whisper back. Not with words, with numbers, with tiny mismatches, with measurements that refuse to land exactly where our best theories say they should. And that is the unsettling part. Because when a number is off by a hair, it is rarely just a hair. It can be a stress test. A quiet warning that the rulebook we rely on might be incomplete. So tonight, we are going to follow that feeling, calmly, carefully, not to chase wild fantasies, but to sit beside a handful of real stubborn puzzles that make modern physics go quiet for a moment. Nothing dramatic, no panic, just a gentle, unnerving thought. What if reality is stable, not because it must be, but because it has been lucky so far? If you enjoy these slow journeys into the edges of what we know, you can softly support the channel by tapping like and subscribing for more bedtime science. And I would love to know, where are you listening from tonight? Now get comfortable and let's begin. For a long time, physics has lived with a rare kind of confidence. Not the loud confidence of someone bragging, the quiet confidence of a structure that has held its weight for decades without bending. It has a name that sounds almost modest for what it is: the Standard Model. If you've never studied physics, you still live inside its success. You live inside the fact that we can predict what happens when invisible things collide at ridiculous speeds. You live inside the fact that we can build machines that depend on quantum rules and have them work reliably day after day, as if nature is following a script. The Standard Model is that script, a rule book that, for roughly 50 years, has explained an extraordinary amount with a kind of precision that feels unreal the first time you see it. It tells us what the basic ingredients are. It tells us how they talk to each other. It tells us which interactions are allowed, and which ones nature simply refuses to do. So, when people say maybe the Standard Model is incomplete, it isn't said lightly. It isn't said for drama. It's said the way you'd say, I think there might be a hairline crack in a beam, after a building has been standing perfectly straight your entire life. Because in this world, one wrong number is never just one wrong number. A small mismatch in a fundamental measurement is not like a typo in a book. It's more like discovering that the ruler you've trusted for decades is not quite the same length as the world. And the W boson sits right at the center of why that matters. The W boson is not a celebrity particle. You don't see it in glossy posters. You don't hear it in casual conversations the way you hear about black holes. But it has a job, a very specific job, a job that makes reality feel stable and predictable. In human terms, you can think of the W boson as a messenger of change. There are processes in nature where one kind of particle becomes another kind of particle. Not metaphorically, literally, a transformation. And the W boson is one of the couriers that makes those transformations possible. It belongs to the weak force, which sounds gentle until you realize it is responsible for some of the most profound changes in the universe, from radioactive decays to the slow chemistry of stars. The weak force is part of why the universe is not frozen in one configuration forever. Now here's where the Standard Model's confidence becomes almost eerie. The mass of the W boson is not just a random property. It is tied into a web of relationships inside the rulebook. If you measure certain other things with enough precision, the W boson's mass is constrained. It should land within a very specific range. So, the W boson becomes a stress test. Because when you measure its mass, you are not only measuring a particle, you are checking whether the whole internal logic of the Standard Model still holds together under pressure. Imagine a bridge you have crossed safely 1,000 times. You trust it without thinking. Then, one day, a sensor tells you one of the main support cables is carrying slightly more tension than it should. Not enough to snap, not enough to make the bridge sway, just enough to make the blueprint and the steel disagree. That's the feeling. The measurement is the sensor. The standard model is the blueprint. And the W boson is one of the cables you can't afford to be wrong about. So, when an experiment comes along and reports a W boson mass that looks heavier than expected, the first response is not celebration, it's suspicion. Because high-energy physics is built to distrust itself. When a result looks exciting, the default assumption is that something went wrong in the process. A calibration error, a statistical fluke, a subtle bias in the selection of events, a background that wasn't modeled correctly. This is not pessimism, it's discipline. It's a kind of self-defense. The history of physics is full of moments where the universe seemed to whisper a secret, and then it turned out to be a loose cable or a mistaken assumption. So the result is studied, questioned, squeezed from every angle. And then comes the part that makes people sit a little straighter, the language of sigma. Sigma is how scientists talk about confidence, but you can feel it more simply if you imagine coin flips. Flip a fair coin 10 times, and you can easily get weird streaks. 7 heads, 8 heads, even 10 heads. It doesn't mean the coin is rigged. It means small samples can create illusions. The more times you flip, the more the average tightens its grip. Randomness has less room to pretend it's a pattern. Physics takes that idea and turns it into a strict culture. A 5 sigma result is often treated as the threshold for saying, this is very unlikely to be a fluke, not impossible to be wrong, but unlikely enough that the community begins to take it seriously. And when you hear numbers beyond that, the emotional message is not, we're sure. It's, if this is noise, then noise has learned how to write sentences. So, when people describe a strong sigma-level discrepancy in a measurement, what they're really describing is the uneasy moment when the usual escape route begins to close. Because the usual escape route is comforting, the usual escape route is, it's probably just statistics. And sometimes it is. But the more confidence rises, the more the story changes from maybe to something is pushing on the system. That's the core terror in a calm suit. If the measurement is correct, then the W boson is telling us that the standard model's internal bookkeeping is missing something. Not a minor correction, a missing influence. Like an invisible weight on a scale. And here is why that lands so hard. The standard model is not a fragile guess. It is one of the most tested frameworks in human history. It has passed checks so precise that most of us don't even have a mental category for how precise they are. So, if a crack appears here, it suggests the crack is not superficial. It suggests that something new might be hiding in plain sight, influencing outcomes without being directly seen. That something could take many forms. It could be a new particle that subtly alters the behavior of the W boson through quantum loops, like a hidden presence that never steps into the light but still changes the room's temperature. It could be a new force, a new symmetry, a new sector of physics that barely touches normal matter, except through tiny, measurable effects. Or it could be a more frustrating possibility that our interpretation of the measurement is missing a systematic detail that imitates new physics. Either way, the message is the same. We are looking at a place where the rulebook is being tested at a stress point. And in a story like this, the most haunting part is not the idea of a spectacular collapse. It's the idea of a quiet mismatch. Because a quiet mismatch can sit for years, like a pressure point that never stops pressing. You can feel the metaphor almost too clearly. Imagine a room you know well. You measure the walls, the corners, the diagonals. Everything should add up. Everything should be consistent. Then one day, you measure again and the room seems slightly smaller. Not enough to notice with your eyes, not enough to bump into furniture, but enough that the tape measure insists. At that point, you have two choices. You can accuse the tape measure, or you can consider that something outside the room is pressing inward just slightly, and the geometry is adjusting. That is what anomalies do to physics. They force you to sit with the possibility that reality is under pressure from something you haven't named. Now, if this were a clean fairy tale, the next line would be, and then we discovered the missing piece. But reality is not that generous. Not quickly. For years, there has been a candidate missing piece that many physicists hoped would make the Standard Model feel less like a miracle and more like an inevitability. Supersymmetry. SUSYR. Even the nickname sounds friendly, like a helpful patch you install to fix a glitch. The idea, in its simplest form, is that many of the particles we know might have partner particles we haven't seen yet, not because nature likes doubling things for fun, but because those partners could smooth out ugly problems in the math. Supersymmetry was attractive for multiple reasons. It could help with deep puzzles about why certain masses are stable instead of ballooning to absurd values. It offered potential candidates for dark matter. It made the overall architecture look like it had an underlying elegance instead of being a collection of coincidences. So naturally, people went searching. And the most powerful place to search is the Large Hadron Collider. Collide particles, smash them together at extreme energies, see what falls out. If supersymmetry is real in a form we can reach, the hope was that something would show up. Some partner particle stepping forward, some clear sign that the universe had indeed hidden a second layer just beneath the first. But the story the LHC kept telling year after year was not a triumphant reveal. It was mostly silence. That silence does not prove supersymmetry is false. Nature does not owe us simplicity. And there are ways SUSY could exist beyond the energies we've probed, or in forms that are more subtle than early predictions. But silence does something psychologically important. It removes the easy patch. It means that when you see a potential crack like the W boson anomaly, you can't automatically say, "Don't worry, the missing pieces are probably SUSY, and we'll find them any day now." Because any day now has already been said for a long time. So, the room feels less decorated with comforting expectations. And that's where this first crack becomes more than a technical footnote. It becomes a mood that says, the Standard Model is astonishingly successful, but it might be sitting on the edge of something we haven't faced yet. And what makes this mood so effective, in the style of the competitor, is how it stays calm. No screaming, no conspiracy, no theatrical panic. Just the steady reminder that physics is a structure of numbers, and those numbers are now being measured with such precision that even tiny deviations begin to matter. Because here's the thing. If you were hoping the universe would tell you its secrets with a loud announcement, it rarely does. It usually does it like this, with a discrepancy, a tension, a value that doesn't land where it should, something that survives multiple attempts to dismiss it. And the longer it survives, the more it starts to feel like a message. Not a message written in words, a message written in the only language the universe seems to speak fluently. Measurement. So, if the W boson really is heavier than expected, the implication is not that our world is unstable tomorrow. The implication is more subtle and more profound. It implies that something else exists, something we haven't directly detected, that is still influencing the outcome. A hidden participant in the equations. And once you accept that possibility, even softly, the mind naturally drifts to an uncomfortable question. If there is a hidden participant here, near the foundations of the Standard Model, what else might be hidden near the foundations of reality itself? Because this first crack is about a specific measurement, a stress test of a trusted rulebook. But the next crack is about something more intimate than a particle. It's about the baseline condition of the universe, the vacuum state that sits underneath everything, like a floor beneath the floor. If the W boson anomaly makes you wonder whether the blueprint has a missing page, the next crack makes you wonder whether the ground itself is perfectly stable, or whether it is resting on a ledge. Not trembling, not collapsing, just not quite as permanent as it feels when you're living on top of it. There's a particular kind of comfort that modern physics gives you. Not emotional comfort, structural comfort. The sense that the universe is not only understandable, but consistently understandable. That if you learn the rules carefully enough, the rules do not change on you when you turn your back. And then you meet the Higgs field. Because the Higgs field is one of those ideas that sounds abstract right up until you realize it is doing something intensely personal. It is participating in the reason you feel solid. It is participating in the reason a chair holds its shape, and your hands do not drift through the table like fog. The Higgs field is not a particle. It is a field, a kind of background presence, a continuous ingredient of reality that fills space the way temperature fills a room. You do not have to believe in it. You can ignore it your entire life. It will still be there, quietly doing its job. The most useful way to picture it is simple. Imagine the universe as a stage with countless invisible settings running underneath the performance. Gravity gives the stage a shape. The electromagnetic field lets light exist and matter bind. And the Higgs field, in a sense, is one of the settings that decides how heavy different actors feel when they try to move. Not by grabbing them like a hand, not by slowing them down through friction, but by defining what it means for them to have mass in the first place. In the Standard Model, this matters so much that without the Higgs mechanism, the math stops behaving like a world you could live inside. Certain particles would remain massless, interactions would look different, and the everyday stability of matter would not come out the same way. So, when the Higgs boson was found, it was treated like more than a discovery. It was treated like a confirmation that the universe had been following a very specific blueprint all along. And the number that came with it, the mass of the Higgs boson, became one of the most watched numbers in all of physics. Because the Higgs mass is not just trivia, it feeds into a deeper question. Is our universe sitting in a truly stable configuration, like a ball at the bottom of a valley? Or is it sitting in a configuration that only looks stable on human timescales, like a ball resting on a shallow ledge, quiet for now, but not guaranteed forever? That second possibility has a name that sounds harmless when you first hear it. Metastability. Metastability is the idea that something can be stable in practice, stable for an unimaginably long time, and still not be the deepest, most stable state available. It's the difference between nothing will happen today and nothing must happen forever. You have seen metastability in ordinary life, even if you never called it that. Supercooled water is a classic example. Water can be cooled below its freezing point and still remain liquid, perfectly clear, perfectly calm, until a tiny disturbance triggers crystallization. The moment the first crystal forms, a wave of change spreads, and the whole system reorganizes into a lower energy state. That is metastability, a system sitting in a temporary calm, not because it is impossible to change, but because it hasn't found the pathway yet. Now, in the context of the Higgs field, this becomes one of the quietest, most unsettling ideas in modern physics. Because the Higgs field is not just any field, it is tied to the structure of the vacuum itself. And the vacuum is not nothing. In quantum field theory, the vacuum is the baseline condition of all fields. It is the ground state, the lowest energy configuration they can settle into. But even that ground state can be complicated, like a landscape with multiple valleys and ridges. The unsettling question is whether the Higgs field's current configuration is the true bottom of reality's landscape, or whether it is a valley that looks like the bottom from where we stand, but is actually perched above a deeper valley separated by a barrier. A barrier that, in classical physics, would be unbreakable unless you had enough energy to climb over it. But classical physics is not the whole story, because quantum physics has a habit of turning barriers into suggestions. And this is where the number enters. The Higgs boson's measured mass is about 125 giga-electron volts, a value that physicists talk about with the casual tone of people discussing weather, even though it's one of the most consequential measurements in particle physics. What makes 125 feel strange is not that it is too big or too small. It is that it appears to sit in a suspicious middle region. There's a simple way to feel this without equations. Imagine three broad possibilities. If the Higgs mass were a bit different, the math suggests the Higgs field could be absolutely stable, a deep valley, the ball at the bottom, no hidden trap door. If the Higgs mass were much heavier, the story could also become stable in a different way, depending on how the other parameters fit together. The exact details are subtle, but the emotional point is clear. There are wide regions of parameter space where the universe looks comfortably locked in. But 125 is close to the boundary between stability and metastability. Close enough that you can't ignore the question. Close enough that you have to say, out loud, in serious physics conversations, it might be stable, or it might be metastable, And the reason that matters is what metastable implies when the system in question is not a cup of water. It is the vacuum itself. If the Higgs field is metastable, then the universe we experience could be a long-lived temporary phase, not fake, not fragile in any everyday sense, but not necessarily ultimate. There could exist a lower energy configuration of the Higgs field that our region of space has not transitioned into yet, and the only way that transition would happen, if it happens at all, is through a mechanism that sounds like a magician's shortcut: quantum tunneling. Quantum tunneling is one of those phenomena that feels like it should be illegal. In the classical world, a ball cannot roll through a hill, a car cannot drive through a wall, a marble cannot appear on the other side of a barrier without crossing it. Classical reality demands a continuous path. Quantum reality is more relaxed about that demand. At the quantum scale, particles are described by wave functions, spread out descriptions of where they might be. And when you have a barrier, the wave function does not always stop cleanly at the wall. It can leak into the forbidden region, decaying, thinning, but not dropping to zero instantly. That leakage is not just math. It produces real effects. It is part of how the sun shines. It is part of why certain kinds of radioactive decay occur. It is part of technologies we use without thinking. Tunneling is not rare. What is rare is when tunneling becomes the mechanism for a global change of state. When tunneling is not about a particle slipping through a barrier, but about a field slipping into a new configuration. So imagine the Higgs field as sitting in a valley separated from a deeper valley by a ridge. In classical physics, the field would need a tremendous push to climb over the ridge and roll down into the deeper state. In quantum physics, it might not need to climb. It might tunnel. A transition could occur without the system ever being at the top of the ridge, just as a tunneling particle is never on top of the barrier in the classical sense. And that transition, if it happened, would not be a loud explosion in the ordinary way people imagine explosions. It would be something stranger. It would be a rewrite, because the Higgs field is woven into the values of fundamental properties. If the Higgs field settled into a different vacuum state, the rules that define particle masses and interactions could change. Not gradually, not negotiably. Change. Inside the new vacuum state, what counts as stable matter could be different. Chemistry could be different. The patterns that allow atoms to be atoms could be altered. So, the imagery that people often use is a bubble of true vacuum forming inside the false vacuum, a bubble of the deeper valley appearing in the landscape. This is called bubble nucleation. Nucleation is the moment a new phase begins, like the first crystal forming in supercooled water, like the first tiny pocket of vapor forming and boiling. In a metastable vacuum picture, you can imagine a tiny region where the field tunnels into the lower energy state, a seed. If that seed reaches a critical size, it becomes energetically favorable for it to grow, and then the bubble expands. Now, pause here, because this is the moment where the mind tries to dramatize. It tries to picture fire, or shock waves, or something cinematic. But the unnerving part of this concept is that it does not need theatrics. The unnerving part is the speed. In many versions of the idea, the bubble wall would expand at near the speed of light, which means there is no meaningful warning. You do not get to see it coming from far away because information about it cannot outrun the thing itself. There is no siren you could build, no telescope you could point. That would let you receive the news early and step aside. If it happened, the first indication would not be a distant flash. The first indication would be that the rules in your location are no longer the same rules. And because this channel's style is calm, we don't need to lean on fear. We don't need to squeeze the listener with panic. We just need to let the logic sit in the open. A near light speed phase transition is not scary because it is violent in a Hollywood sense. It is scary because it is indifferent. It is a change that does not ask permission and does not announce itself in advance because physics does not have a system for announcements. The universe does not send warning emails. It just follows what is allowed. Now, the immediate question that a grounded listener should ask is this: if this is a serious possibility, why are we still here? And that is where the story becomes almost paradoxically soothing. Because metastability, if true, can still imply lifetimes vastly longer than the current age of the universe. Metastable does not mean about to go. It can mean effectively stable for everything humans will ever experience. A ledge can be so broad and so deep that, for practical purposes, it behaves like a valley. And the calculations many physicists discuss suggest that if the standard model is taken at face value, the vacuum's lifetime could be enormous. So why call it a crack at all? Because the real crack is not a doomsday prediction. The real crack is the philosophical discomfort of living in a universe that might be balanced on a boundary. The discomfort of realizing that the deepest stability might not be guaranteed by the simple version of the rulebook. And the discomfort of noticing that the Higgs mass is not just anywhere. It is near the edge. It's as if nature has dialed the parameters to a region where the question cannot be dismissed. Now, there is a second layer to the story, and it matters in the same way the W boson story mattered. Because the moment you see a potential instability, you want new physics to come in and stabilize it. You want an extra ingredient to appear and reshape the landscape so that the ledge becomes a true valley. This is where, again, people look to theories like supersymmetry or other beyond standard model ideas to modify the running of parameters at high energies to make the vacuum more comfortably stable. And again, the universe has not been eager to cooperate. The LHC has not delivered a simple, clean new set of particles that solves everything with elegance. So, you are left with an uncomfortable purity. The standard model works brilliantly, but when you extrapolate it to very high energies, it begins to whisper strange things about the Higgs potential. And if the standard model is not the full story, then the Higgs mass might be hinting at what is missing. Not by telling you directly, but by placing you in a situation where stability depends on details you do not yet know. That is why this crack belongs in a list like ours, because it is not a random curiosity. It is a place where our best-known physics, taken seriously, points to a knife edge. Now, let's make the landscape image more vivid, because it's the cleanest way to keep this intuitive. Picture a rolling landscape in the dark. You cannot see the whole thing, only the ground under your feet. You feel flat ground, you feel safety, you build cities. But then someone brings a sensitive instrument, a kind of mathematical flashlight, and shines it outward. The flashlight is not made of light. It is made of extrapolation, calculation, renormalization, group flow. The way parameters evolve with energy scale. And that flashlight suggests that the flat ground might not extend forever. It might curve gently upward into a ridge, and beyond that ridge might be a deeper drop. You can still live your whole life without ever reaching the ridge. The ridge might be unimaginably far in energy scale, not distance scale. It might be relevant only in conditions like the early universe, or in extreme regions like black holes, or in hypothetical high-energy processes. But the fact that the ridge might exist changes how you think about the ground. It turns stable because it must be into stable because it has been so far. And that shift in a scientific mindset is enormous, because it implies there is no absolute guarantee in the simple model. There is only probability and timescale. Now, even this needs one more calming correction. When people hear about vacuum decay, they sometimes assume humans can trigger it by doing experiments. That idea spreads because it is narratively satisfying. It makes the story feel like a cautionary tale. But mainstream physics does not treat particle colliders as existential threats in that way. The energies in cosmic rays striking Earth's atmosphere can exceed what colliders do, and the universe has been running those collisions naturally for billions of years. So, the story here is not, we might cause it. The story is what our equations imply about the vacuum structure, and what it means that the Higgs mass sits near a boundary where the question exists at all. That is the mood, calm, precise, unnerving in a quiet way. And notice what has happened across the first two cracks. The first crack said, one measurement, one key number, might not land where the rulebook says it should. The second crack says, even when the rulebook lands perfectly, the rulebook itself might imply that the deepest foundation of reality is not in the most comfortable state. One crack is a mismatch. The other is an implication. and both of them point to the same meta message. The standard model is incredibly successful, but it may not be the final story. Now, before we drift forward, it helps to take the two ideas we've built and hold them in one hand. WLS boson tension, if real, suggests unseen influences in the particle zoo. Higgs metastability, if real, suggests the vacuum's stability depends on unknown details at high energies. One is a stress test of a beam. The other is a survey of the ground beneath the beam. And together, they set up the next uncomfortable thing. Because once you start talking about the vacuum, the conversation naturally slides into a puzzle that is not just, is it stable? It becomes, what is the vacuum worth? What is the energy of empty space supposed to be? And why do our calculations disagree with reality by a number so large it becomes almost meaningless to say it out loud? That next crack is not about a ledge. It is about a mismatch so violent that it makes metastability feel almost gentle. So for now, let the Higgs story settle the way it's meant to, not as a fear, as a subtle change in how you label certainty. Because the calm truth is this: the universe can be safe, familiar, and reliable, and still be sitting in a configuration that is not mathematically guaranteed to be ultimate. It can be a long-lived phase, a stable habit, a beautiful arrangement that holds together, not because it is the only possible arrangement, but because it is the one that has lasted long enough for minds like ours to appear and notice it. And if that idea feels a little dizzying, that's normal. It is the sensation of standing on something that still holds your weight, while realizing that holds and must hold forever are not the same word. There's a question that sounds like a joke until you try to answer it carefully. If you took a perfectly sealed box, pumped every last atom out of it, and left only empty space inside, would that box weigh less? Most people instinctively say yes, because we treat emptiness like zero, like a blank page, like a room after the furniture is gone. But modern physics hesitates, because in quantum field theory, empty space is not a blank page. It is more like a page that is never truly blank, no matter how clean you wipe it. The ink is still there, faintly in the paper itself. And that faint ink has a name: vacuum energy. The simplest way to feel it is to remember what a field is in this story. A field is not a cloud of particles floating around. It's the underlying thing that particles are made from. The electromagnetic field is there even when there are no photons passing through. The electron field is there even when you have removed every electron from a region. The fields remain because the universe is built out of fields. So, what does empty mean in a universe made of fields? It means the fields are in their lowest energy state, their ground state. And the strange part is that even the ground state is not perfectly still. Quantum mechanics does not allow a field to sit absolutely motionless at a single exact value everywhere with zero wiggle. Not because it is busy, but because the rules of the game do not permit perfect stillness. There is always a minimum amount of restless motion, a soft jitter in the baseline. Not dramatic, not visible, but real in the mathematics and real in the consequences. This is where the first crack appears. Because if vacuum energy exists at all, it should contribute to gravity. Energy gravitates. That's one of the most reliable lessons from relativity. If you have energy in a region of space, it curbs space-time. It behaves like weight, even if it doesn't look like a pile of rocks. So if empty space contains even a tiny amount of baseline energy, then empty space should have a gravitational effect. And if empty space contains a large baseline energy, then empty space should dominate the universe's behavior. It should either yank everything together or blow everything apart at a pace that makes galaxies impossible. Yet here we are. The universe is expanding, yes, but it is not exploding into nonsense in the way the raw quantum estimate would suggest. This mismatch is not a minor disagreement. It's not a rounding error. It is not an argument about measurement technique. It is a canyon. In the simplest, most naive calculation, if you add up the vacuum energy contributions from quantum fields, you get a number that is absurdly large. And when cosmologists infer the vacuum energy density from observations of the universe's accelerated expansion, they get a number that is incredibly small. The ratio between those two expectations is often described as about 10 to the power of 120. That is not a typo. It is one followed by 120 zeros. It is so extreme that it breaks the normal human sense of what disagreement even means. If you tell someone, my measurement is off by a factor of 2, that's a problem. If you tell someone, it's off by a factor of 1,000,000, that's a crisis. If you tell someone, it's off by a factor of 10 to the 120, that's not a crisis anymore. That's a signal that the frame itself is wrong. It's like trying to use a ruler to measure a room and discovering your ruler is longer than the observable universe. You don't correct the measurement. You question the ruler, the room, and the meaning of length. Now, here is what makes this crack feel uniquely unsettling. The earlier cracks felt like something might be missing. This one feels like something might be fundamentally misunderstood, because the vacuum is not a side detail. It's the stage floor. It's the baseline of all fields. It is the quiet zero level that everything else is measured against. And our best theory of the small, when asked to predict the weight of that quiet zero, produces a number that would make the universe violently unrecognizable. And yet the universe looks calm enough for stars to burn steadily for billions of years. So, the first thing to do is to make sure we're not talking in fog. What do we actually observe? We observe that the expansion of the universe is accelerating. Galaxies are not just moving apart due to the initial push of the Big Bang. On large scales, the rate of separation is speeding up. This is often described as being driven by dark energy. And the simplest form of dark energy is a cosmological constant, which behaves like a constant energy density of empty space. In that simplest picture, the vacuum has a tiny but non-zero energy density that acts like a gentle pressure, pushing space-time to expand faster over time. And when you fit this to data, the value is small. Not zero, but small. Small enough that it only becomes dominant on cosmic scales, over billions of years, not in your living room. So far, so good. The crack appears when you ask, where does that small vacuum energy come from? Because quantum field theory offers many contributions to vacuum energy, not just one, many. And there's no obvious reason they should cancel to produce the tiny observed value. It's like walking into a room with 1,000 loud fans and being told the total sound level is almost silence, because their noises cancel almost perfectly. You could imagine it happening by coincidence once, but when it needs to be perfect to 1 part in 10 to the 120, coincidence stops feeling like a real explanation. Now, in the history of physics, whenever a number comes out wrong, you look for a missing ingredient. Maybe there's a symmetry that forces cancellations. Maybe there's a new field. Maybe the calculation is missing a piece of the puzzle. Maybe gravity itself changes at certain scales. And people have tried all of these avenues in one form or another. But what makes this problem sting is that we don't have a clean, universally accepted resolution. Not one that feels like the standard model felt. Not one that makes you say, oh, of course, it had to be that way. Instead, we have a menu of options, and most of them feel like compromises. One option is that the vacuum energy is naturally huge, but something cancels it almost perfectly. This is technically possible, but it feels like fine-tuning, like balancing a pencil on its tip and calling it a stable arrangement. Another option is that our way of adding up vacuum energy is not the right way to connect quantum fields to gravity. That begins to smell like quantum gravity, the still missing bridge between our theories of the small and the large. Another option is that the cosmological constant is not constant at all, but a slowly evolving field. That's a different kind of story, but it still needs to explain why the energy scale is so tiny compared to the raw quantum expectation. And then there's the option that, in a way, is the most psychologically unsettling. The option that says the vacuum energy is not determined uniquely by deep theory. It varies across a larger multiverse of possibilities. And we happen to live in a region where it is small enough for complex structures to exist. This is where the anthropic principle enters, and it enters like a quiet trapdoor. The anthropic principle, in its mild form, is simply a selection effect. You can only observe a universe compatible with observers. You won't find yourself in a place where the laws instantly erase the possibility of chemistry, because then you wouldn't be there to notice. That mild statement is almost trivial, The trouble begins when it becomes an explanation. When someone says, the vacuum energy is small because if it weren't small, you wouldn't be here. It sounds like it explains something. It sounds like wisdom, but it also sounds like a loop. It risks becoming, the universe is this way because it has to be this way for us to ask why it is this way. That's not the kind of explanation physics usually celebrates. It doesn't feel like a mechanism, it feels like survivorship bias turned into metaphysics. And yet it keeps coming back, because the cosmological constant problem is so extreme that it pushes people toward extreme solutions. If the vacuum energy can take many values across many regions, and if most values lead to sterile universes with no galaxies, no stars, no chemistry, then observers would only appear in the rare regions where the vacuum energy is small enough to allow structure. In that story, we are not special, we are selected, not by intention, not by design, just by the fact that only certain settings allow anyone to be around to read the settings. And this is the point where the tone of the crack changes, because now physics begins to sound like a casino. Not in the sense of gambling with your life, but in the sense of a vast space of possibilities, most of which are empty of meaning, and a tiny fraction of which happen to permit complexity. A multiverse becomes a kind of landscape of failed attempts, universes that expand too fast for matter to clump, universes that collapse too quickly for stars to form, universes with constants just slightly different, where chemistry never stabilizes. A graveyard of possibilities. And our universe in that frame is not the default. It is a surviving bubble. Now, notice how this connects back to what we already built with the Higgs metastability story. There, we imagine the vacuum as having multiple states, with transitions possible through tunneling. Here, we imagine the vacuum energy as a value that might not be uniquely fixed by deep logic, but might vary across a broader reality. These are different concepts, but they rhyme. They both make the vacuum feel less like a single stable floor, and more like a landscape of potential floors. And that is why this is crack number 3, because the vacuum is the closest thing physics has to the background. If the background is uncertain, if the baseline cannot be predicted cleanly, then the feeling that we understand the world begins to change. It's no longer that we don't know what's inside the machine. It's that we may not know why the machine's idle setting is what it is. Now, to keep this grounded and honest, there's a key nuance that matters. When physicists say 10 to the 120, they are not always describing one single precise calculation. The exact number depends on how you define the cutoff scale, how you treat contributions, and the framework you use. But the core point survives every nuance. The mismatch is staggeringly huge, and it remains one of the most notorious unsolved problems in theoretical physics. Not because it is a philosophical curiosity, because it's a place where our most successful frameworks clash violently. Quantum field theory wants the vacuum to be heavy. Cosmology observes the vacuum to be almost weightless. Both frameworks have enormous empirical success in their own domains. But when you ask them to agree on the weight of nothing, they do not agree. And the universe calmly continues expanding. So, what does a competitor-style story do with a crack like this? It doesn't turn it into a lecture. It turns it into a feeling, a simple feeling, that the emptiest thing in the universe is not empty, and that the most basic number, the energy of nothing, is the number we understand the least. That's the unsettling calm of it. You can build a transistor. You can predict particle interactions to ridiculous precision. You can land probes on distant worlds. And yet, when you ask, how much does nothing weigh? Physics answers with two numbers that cannot both be right, and no one knows how to reconcile them in a satisfying way. Now, if you sit with that long enough, it naturally raises another question. If vacuum energy is so mysterious, what does that say about gravity? Because gravity is the language that translates energy into geometry. Gravity is the part of the story that decides whether energy curves space-time gently or violently. And in this crack, gravity is not a hero saving the day. Gravity is the judge in the courtroom, staring at two contradictory testimonies. Quantum fields insist the vacuum should curve space-time catastrophically. The cosmos insists the curvature is tiny. Gravity is the place where the contradiction becomes physical. which leads directly to a kind of quiet suspicion. Maybe gravity is not behaving the way we think at the deepest level. Maybe the reason this problem is so stubborn is that we are trying to glue two theories together with the wrong conceptual adhesive. Maybe gravity is weaker than it should be, or leaks into places we don't see, or changes character at scales we haven't tested. And that suspicion brings us to the next crack, the one that sounds like a simple observation but hides a deep puzzle. Gravity is absurdly weak compared to the other forces, so weak that a small magnet can win a tug-of-war against the entire planet. So weak that it feels less like a fundamental force and more like an afterthought. And if gravity is that strangely weak, then the vacuum energy problem starts to look less like a random glitch and more like a message. Not a message written in words, a message written in imbalance, a hint that the deepest structure of the universe is still holding something back from us. For now, let this crack do what it's meant to do. Not to frighten, not to overwhelm, just to adjust your sense of certainty. Because once you realize that nothing is not nothing, the universe becomes slightly stranger in a quiet way. And once you realize we can't explain why empty space weighs what it weighs, the floor under the theory doesn't feel as final. It still holds, but it feels just slightly like it has hidden seams. There's a small fact about gravity that should feel impossible the first time you really notice it. You can hold a cheap refrigerator magnet between two fingers. You can press it to a door, and with a gentle tug, that magnet can lift a paperclip against the pull of the entire Earth. Not because the paperclip stopped having mass, not because gravity turned off, but because gravity, compared to the other forces, is shockingly weak. It is so weak that everyday objects can casually defeat it in tiny local battles, while gravity still rules the largest structures in the cosmos. And that split personality is not just a poetic observation. It is one of the deepest technical headaches in modern physics. Because if gravity is fundamental, if it is truly part of the same family as the other forces, then why does it show up at such an absurdly different strength? This is sometimes called the hierarchy problem, and even the name sounds like a polite label for something that should keep you awake. A hierarchy is what you build when you understand how the levels relate. But in this case, the hierarchy looks less like a neat staircase and more like a cliff. One way to say it, without drowning in equations, is this: the forces that govern the particle world, electromagnetism and the nuclear forces, operate at energy scales that feel close to human technology. Close enough that we can build machines to probe them, to measure them, to stress them. Gravity, by contrast, seems to wake up at a scale that is unimaginably higher. A scale so high that it's not just beyond our machines. It's beyond the entire design philosophy of machines. If you put the strength side by side, the gap is commonly summarized as something like a factor of 10 to the 36, a 1 with 36 zeros. That number is not meant to be memorized. It's meant to make you feel the distance. Because in physics, when you see a number like that, you suspect one of two things. Either there is a protective principle we haven't discovered yet, or we are misunderstanding the architecture. And this is where the fourth crack opens, because there's a strange, almost mischievous possibility that keeps showing up in the literature and in the imagination of theorists. Maybe gravity is not weak because it is inherently weak. Maybe gravity is weak because it is leaking. Not leaking in a sloppy metaphorical way. Leaking in the most literal way our best math allows, into dimensions we do not see. Picture the world you experience as a kind of surface. Not a flat sheet, but a three-dimensional space you can move through, filled with matter and light and electromagnetic fields. Now imagine that surface is embedded inside something larger, a higher dimensional bulk, like an ocean surrounding a thin membrane. In this kind of scenario, everything you are made of, electrons, quarks, photons, the entire standard model, is pinned to the membrane. It can move freely along the membrane, but it cannot leave it, like ink trapped in the fibers of paper. But gravity is different. Gravity, in some models, is not perfectly pinned. Gravity can reach into the bulk. It can spread out. And if it spreads out into more directions than the other forces can access, it becomes diluted on our membrane. Not because it lost its nature, because it lost its concentration. That's the core intuition behind what people loosely call brain world ideas. A brain, short for membrane, is the surface-like universe where the standard model lives, and the bulk is the larger space beyond it. On the brain, electromagnetism still feels strong because it has nowhere else to go. It is trapped with us. But gravity, if it can wander into the bulk, doesn't stay focused. It bleeds away, which means that from our perspective, gravity looks weak. Not because it is weak everywhere, because we are seeing only the thin slice of its full presence. This idea is haunting because it takes the hierarchy problem and reframes it as a geometry problem. Instead of asking, why is gravity so small, it asks, why are we only receiving a fraction of it? And if you let yourself sit with that for a moment, you realize why this becomes a crack in the foundation. Because it suggests that the universe you see might not be the whole arena. That the reason gravity doesn't match the other forces is not an internal mismatch, but an external one. A mismatch between what is allowed to exist in our layer of reality and what is allowed to roam outside it. Now, it's important to keep one foot on the ground here. These brain and extra dimension models are not confirmed facts. They are attempts, bold attempts, but they are attempts motivated by the scale of the problem. Because when the gap is that huge, you start entertaining possibilities that would otherwise sound like science fiction. And here's the key point for our story. If extra dimensions exist, they might not be large like a hidden corridor you could walk into. They might be curled up, or warped, or structured in ways that make them invisible to everyday experience. And the only way you'd notice them is through subtle missing effects. Tiny mismatches, energy that doesn't add up, particles that recoil as if something unseen bumped them. In other words, you wouldn't see the extra dimension directly. You would see the shadow it casts on conservation laws. And this is where CERN enters again, not as a rumor factory, but as an accountant. Because the Large Hadron Collider is not only smashing particles, it is tracking balances. It is doing the physics equivalent of watching a billiards table and making sure the total momentum adds up after every collision. If something carries momentum away, something you cannot detect, the visible debris will look lopsided, like a bank statement with a clean list of deposits and withdrawals, and then one transaction labeled simply missing. This is why particle physicists care so much about a phrase that sounds painfully technical but is actually very intuitive. Missing transverse energy. Here's the idea in plain language. In a collider, two beams come in opposite directions and collide. Most of the interesting action happens perpendicular to the beam line, sideways from the perspective of the detector. If the detector sees particles flying out in one direction, it should also see something balancing them out in the opposite direction, because momentum in that sideways plane should be conserved. So when the outgoing spray doesn't balance, when there's a clear push in one direction without an equal push the other way, physicists call that missing transverse energy. It's the signature of something invisible taking energy and momentum out of the collision. And this is where the brain world picture becomes operational, not just philosophical. Because if gravity can access extra dimensions, then perhaps gravitons, if they exist as quantum carriers of gravity, could slip into the bulk. They wouldn't be trapped on our brain the way photons are. They could leave, and if they leave, the detector won't catch them. The collision would look like a magic trick. All the visible particles would behave as if someone quietly opened a door in the lab and carried a bag of momentum out into a hallway no one can access. Now, again, this is not a confirmed observation, but it is exactly the kind of thing collider experiments are designed to test. Not by seeing the extra dimension, by noticing whether nature's bookkeeping fails in a particular pattern. And that's why this crack belongs in the same lineup as the others. Because it points at a type of evidence you can actually go hunting for. Not a dream, not a metaphor, a measurable imbalance. If energy goes missing in a consistent way that cannot be explained by known particles, it raises a disturbing possibility. Maybe something real is leaving our universe's visible layer, not leaving the universe in the sense of going far away, but leaving our accessible sector of reality. And the unsettling part is that this is exactly the type of doorway you would expect if extra dimensions exist. You would not find a literal portal. you would find missing. Now let's fold in the second piece of Act 4 because it clicks into place almost too neatly. Dark matter. Dark matter is one of those words that people have heard so often it starts to sound like a genre. But in astronomy, it is stubbornly specific. Galaxies rotate too fast for their visible matter to hold them together. Clusters of galaxies bend light in ways that suggest more mass than we can see. The large-scale structure of the universe grows as if there is extra gravitational scaffolding. And yet, despite decades of searching, we have not confirmed what dark matter is made of. No confirmed particle. No confirmed detection that everyone agrees on. Just gravity. Gravity that behaves as if there is an extra mass, but no light. So, the question becomes, what if dark matter is not a new kind of particle in our brain at all? What if it is matter somewhere else? Close enough to affect gravity, but not close enough to share light. In a brain world picture, you can imagine multiple brains, like parallel membranes in a larger bulk. They might be separated by a tiny distance in an extra dimension we cannot access. From our point of view, they would be right here, overlapping our space, but not interacting electromagnetically. Their photons would be trapped on their brain, not ours. Their electrons would be trapped on their brain, not ours. So, we would not see their stars, we would not see their dust, we would not see their planets, but their mass would still curve space-time. Because gravity, in the brain world story, is the one thing that can reach across the bulk, which means their mass could tug on our galaxies. It could shape our cosmic structure. It could act like a ghostly partner, a neighbor you can feel but never see. That's why this idea sometimes gets described, half-jokingly, as poltergeist mass. Not because it's supernatural, because it behaves like the gravitational influence of something invisible, like footsteps upstairs in a house you thought was empty. Now, to be fair, there are many competing explanations for dark matter that do not require extra dimensions. There are particle candidates. There are modifications to gravity. There are complex astrophysical effects. The point here is not to declare a winner. The point is to show you why this crack is so compelling in a competitor-style narrative. Because it ties together multiple mysteries with one eerie geometry. Gravity is weak because it leaks. Energy disappears at colliders because it slips into the bulk. Dark matter appears as extra mass because it belongs to a neighboring sector we cannot illuminate. When a single conceptual move starts stitching together several missing pieces, it becomes tempting. And that temptation is exactly the feeling we want to bottle. Not certainty, not a conclusion, a pressure, a sense that the universe might have hidden compartments. Now, let's slow down and ask the most important question you can ask at this point. If this were true, why haven't we noticed extra dimensions already? Why doesn't gravity behave weirdly in your everyday life? Why doesn't the Earth suddenly lose some of its pull because gravity ran off into a new direction? And this is where the details get subtle, and also where the story becomes more elegant. Because the brain world idea doesn't usually claim that gravity disappears locally. It claims gravity's field lines, so to speak, can spread out differently at different distances. At everyday scales, gravity looks normal. At very short scales, it might deviate. At very high energies, like those reached in particle collisions, you might excite modes that can access the bulk. In other words, the leak might not be obvious in the calm world. It might only reveal itself under stress, under compression, under conditions that mimic the early universe. That's why the LHC matters in these stories. It is, in a controlled way, a device for pushing reality to its edges and watching which rules remain strict. And this brings us back to that hierarchy number, the one with 36 zeros. Because the hierarchy problem is not just a complaint about gravity, it's a warning sign. When a force is that different from the others, you suspect it is not playing by the same rules. Or it is playing by the same rules, but on a bigger board. A board with more directions. A board with more room for its influence to spread. And if gravity is on a bigger board than the standard model, then our entire intuition about what the universe is, and where it is, starts to wobble. Because then, space is not just the space you can see. It is the bulk. And what we call the universe might be a surface phenomenon, like weather on an ocean. Real, physical, complex. But not the full volume of the world. Now, there's another quiet layer here that makes this crack feel especially sharp. If gravity can leak, then the conservation laws we trust might still hold globally in the full higher dimensional space, while appearing to be violated locally on our brain because we're not tracking the whole system. It's not that physics breaks, it's that we are watching only a subset of physics, like listening to a duet while wearing one earplug and insisting the melody is incomplete. The melody is complete. We are incomplete. And this is where the emotional tone shifts again, because all the previous cracks hinted that our theories might be missing ingredients. This crack hints that our reality might be missing context. Not missing in the sense of lacking, missing in the sense of being a slice, a layer, a page torn from a larger book. And once you accept even the possibility of that, you start asking a new kind of question. If gravity can reach across layers, what else might be influencing us from beyond what we can see? Not in a mystical way, in a strictly physical way, a tug that doesn't come from any visible object, a drift that can't be explained by known mass inside the observable region, a large-scale motion that seems to have a direction, like a current. And that question leads naturally into the next crack, because there is a cosmic scale version of something is pulling us that shows up in the language of astronomy. A hint that entire structures might be moving in a coordinated way, as if responding to an influence we have not fully mapped. A flow, a pull, a gravitational whisper from beyond our comfortable horizons. So, if you want the clean takeaway from this fourth crack, it's this. Gravity is the only force that consistently behaves like it's playing on a bigger stage. So either we haven't understood why it is so different, or we haven't yet seen the whole stage. And when you listen to the universe through that lens, the next thing you notice is motion. Not the motion of a single galaxy, but the motion of many, as if the cosmos itself is drifting slowly towards something unseen. There is a kind of comfort in believing the universe is only doing what we can account for. A galaxy spins because of the matter inside it. A cluster drifts because of the gravity we can map. A direction in the sky is just a direction, not a destination. And then you look at the motion of many galaxies at once, and you notice something that feels coordinated. Not the normal, messy kind of motion you'd expect from random cosmic history, but a subtle sense of alignment, a shared drift, a current. Astronomers have a name for the broad idea behind it: bulk flow. A flow not of water, but of galaxy clusters moving together, as if the local universe is sliding across a deeper gravitational landscape. If you imagine standing on a calm beach and suddenly realizing the entire ocean is moving, slowly, in one direction, not as waves, but as a tide you didn't know existed, that's the emotional shape of this crack. Because the standard story says this: on the largest scales, the universe is expanding. On the smaller scales, gravity clumps matter into galaxies and clusters, and the random bumps left over from the early universe create a pattern of motion we can statistically predict. So, when we see galaxies moving in a way that seems more unified than expected, the first instinct is simple. Maybe we haven't measured perfectly. Maybe we're confusing local motion with global motion. Maybe the data is biased by the way we look. And sometimes that's exactly what happens. But the reason this becomes a crack in stories like ours is that the question refuses to fully die. It keeps resurfacing in different analyses, different catalogs, different eras of measurement, as if the universe itself is gently insisting, you are not done with this. Because here's the nightmare version of the thought. What if there is a gravitational pull influencing our region of space from beyond what we can see? Not beyond in distance alone, but beyond in the practical sense. Beyond the limits of our sky maps, beyond the boundaries of where our surveys can confidently count what's there. A tug from outside our comfortable accounting. And once you allow that possibility, even for a moment, it changes the vibe of the cosmos. The universe stops feeling like a closed book. It starts feeling like a room with a door you haven't opened. Now, to understand the shape of the mystery, you only need one key idea. We don't just sit still in the universe. We move relative to the cosmic background. We can measure that motion, for example, by looking at the cosmic microwave background, the CMB, and noticing a dipole pattern that tells us we're moving with respect to that ancient light. This is normal. Motion happens. But the deeper question is what drives the motion of galaxies and clusters beyond our local neighborhood. If you take a big enough volume of space, on average, things should smooth out. Random pulls should start canceling. The universe should behave like a fair coin over long enough sequences. So, when researchers talk about a dark flow or an unexpectedly large bulk flow, what they're really saying is this: the coin might not be fair, or we may be looking at a smaller slice than we think, missing the heavier weight that's shaping the toss. And that leads directly to an older, more grounded piece of this story: the Great Attractor. Even the name sounds like mythology, but it began as something straightforward. Astronomers noticed that galaxies in our region weren't just moving with the expansion. They were drifting toward a particular patch of sky as if something massive was pulling. That something turned out to be associated with structures in the direction of what's sometimes called the zone of avoidance, a region partly obscured by the plane of our own Milky Way. Dust and stars in our galaxy block our view, making it harder to map what's behind. So, for a while, it was possible to say, maybe the mass is there, we just can't see it well. A hidden mountain behind fog. And as surveys improved, the picture sharpened. There is indeed a concentration of mass in that direction. Large-scale structures, clusters, superclusters. Nothing supernatural, just gravity doing what gravity does. But here is where the crack widens. As the maps got better, it looked like the Great Attractor wasn't the whole story, not the full explanation for the motion. Like finding a big weight on one side of the scale, and still watching the scale tilt even further than that weight should cause. So, the explanation expanded outward. Maybe the motion is influenced by an even larger structure beyond the Great Attractor. And that line of thought points toward another enormous region, the Shapley supercluster, a truly massive concentration of galaxies. One of the biggest structures in our local cosmic neighborhood. A plausible source of pull. A better candidate, some argued, for explaining parts of the observed drift. And yet, depending on which measurements you trust and how you model the motion, the story still doesn't always fully close. It becomes a chain of explanations that keep stepping back. Great Attractor, then Shapley, then maybe something else. Then maybe the statistical expectation is wrong. Then maybe our window is biased. Then maybe. And that maybe is the feeling. Because this crack isn't just about one object. It's about the possibility that the large-scale universe might have patterns we haven't fully accounted for. Patterns that could hint at something beyond the visible horizon of our measurements. Let's say it gently, in the way a bedtime science channel should. We do not see the entire universe. We see the observable universe, a sphere defined by how far light has had time to travel since the beginning. There is nothing special about the boundary of what we can observe, except that it is the boundary of our information. Reality does not end there. Our data does. So if there were extremely large-scale structures beyond our horizon, they could still, in principle, influence our region gravitationally. But even saying that out loud introduces tension, because it touches the edge of a deeper question. How can something outside the observable universe affect us without violating causality? Is gravity instantaneous? No. In modern physics, changes propagate at the speed of light. So any influence we feel must have had time to reach us. Which means if we're being pulled, that pull has a history. It was set up long ago, in the early distribution of mass energy. A kind of cosmic inheritance. And this is where the dark flow idea becomes especially provocative in a competitor-style narrative. Because it sounds like evidence of a mismatch between our assumption of large-scale homogeneity and what the data might be whispering. That mismatch could be a measurement artifact, or it could be a hint that the early universe had features bigger than our observable patch, leaving a residual drift. Or, in the more speculative corner, it could point to interactions beyond our standard cosmological picture. And once you step into that speculative corner, another set of ideas waits there, quietly. Ideas that treat the Big Bang not as a singular beginning from nothing, but as a kind of event, a collision, a rebound, a contact between larger structures. In some models, our universe is like a membrane in a higher dimensional space. That word again, a brain. And the Big Bang is not the birth of everything, but the aftermath of two brains interacting, touching, colliding, releasing energy into our brain in a way that looks, from inside, like a hot beginning. This family of ideas is often associated with cyclic or ekpyrotic cosmologies. And the reason it belongs here, in this act, is not because we are claiming it is true. It belongs because it offers a narrative logic that matches the mood of the crack. If the universe is not a single isolated object, but a layer in a larger setting, then large-scale motions and anomalies stop being purely internal puzzles. They become potential bruises, potential echoes, potential signs that our universe has been shaped by contact with something beyond itself. In a story like ours, you don't need to push the details. You just need the image. Two vast surfaces, drifting through a higher dimensional ocean. A near miss, a gentle impact, a transfer of energy so enormous that beginning becomes a local description. And if that sounds far away from galaxy flows, here's the subtle connection. A brain world picture naturally invites the possibility of large-scale coherence. If the bulk has structure, if brains can carry large-scale features, if collisions imprint patterns, then the universe might inherit a preferred direction, or a large-scale gradient that survives as motion. Again, not proven, but emotionally consistent, a way of making the crack feel like it belongs to the same building. And even if you never accept the brain collision idea as literal, it serves a purpose. It reminds you that the largest motions we measure might not be explainable by local objects alone. They might be the kind of thing that only makes sense when you zoom out beyond our habitual frame. This is the point where many viewers feel the shift. Because earlier cracks felt like problems in equations, this one feels like a problem in perspective. It makes you wonder if our map of the universe is like a flashlight beam in a cavern, bright where it shines, but surrounded by dark. And in the dark, you can't rule out a slope in the floor. You can't rule out a massive presence just outside the circle of light. So, what do we do with this? We do the honest thing. We hold it as a tension. We acknowledge the known facts. Galaxies have peculiar velocities, large structures create flows, the Great Attractor and the Shapley region are real concentrations of mass, and much of the motion can be explained by mapped structure. And then we admit the lingering unease that keeps the crack open. The possibility that the story still has edges we haven't measured cleanly. That the universe might have a subtle drift we don't fully understand. A current beneath the surface. And that current, whether it is real or illusory, sets up the next kind of question perfectly. Because once you start looking for large-scale fingerprints, once you start asking whether our universe carries scars from earlier conditions, your attention naturally turns to the oldest light we can see. The cosmic microwave background, the baby picture of the universe. Because if there was ever a place for a bruise to show up, it would be there. And in that ancient map, there is one feature that has been bothering cosmologists for a long time. A cold spot, a region of sky that looks just a little too different from what the simplest model would predict. Not dramatic enough to be an obvious error, not clean enough to dismiss, just strange enough to feel like the universe left a thumbprint where it shouldn't have. So after you feel the drift of galaxies, after you sense the pull without a clear source, it's almost inevitable that you end up staring at the oldest backdrop of all, and asking whether that cold spot is just statistical noise, or whether it's the mark of something that once touched our universe from the outside. There is a special kind of unease that arrives when you stop arguing about individual objects and start wondering if the entire sky has a memory. Because once you've entertained the idea of a large, coherent drift in the motion of galaxies, the next thought comes naturally. If something truly unusual happened to our region of reality, long before galaxies even formed, it would not announce itself with a headline. It would show up as a faint statistical fingerprint, a tiny imbalance that shouldn't be there. And there is exactly one place we can look for fingerprints that old: the cosmic microwave background. The CMB is often described as the oldest light in the universe, a leftover glow from when everything was hot enough that light couldn't travel freely, and then, suddenly, it could. A kind of afterimage, a baby photo, not a picture of stars or galaxies or planets, a picture of the universe before it had any of those things. Which is why, when something looks odd on that map, it feels different than an ordinary mystery. A galaxy can be messy, a star can be strange, a measurement can be wrong. But the CMB is supposed to be simple in a very specific way. Nearly uniform, nearly perfect, and yet not perfectly uniform. There are tiny temperature differences across the sky, and those tiny differences are not a flaw. They are the seeds. The slight overdensities that eventually became galaxies. The slight underdensities that became cosmic voids. The CMB is smooth enough to be almost boring, and that's the miracle. And then, in the middle of that calm, there is one patch that has drawn attention for years. A cold spot, a region of sky that appears cooler than the surrounding areas by an amount that stands out as unusual compared to simple expectations. Not so extreme that it screams new physics, but just odd enough to whisper, look again. The first reaction is the most human one. Maybe it's a mistake. Maybe it's dust in the way, foreground contamination, some artifact of the instruments, some subtle bias in how we subtract the Milky Way's glow. Because the universe is not the only thing making microwaves. We have our own messy environment, our own galaxy, our own local clutter. And early on, that was a reasonable suspicion. In stories like this, the cold spot begins as something you can dismiss. A smudge on the lens, a coffee stain on the ancient photograph. But the unsettling part is that it doesn't neatly disappear. As measurements improved and analyses became more careful, the cold spot kept existing as an object of debate, not universally accepted as a deep anomaly, not universally dismissed as nothing. It just stayed in that irritating middle category, the category that creates sleepless curiosity. Now, the sober explanation that often comes first is simple. Maybe it's caused by a void, a large region of space with fewer galaxies than average, lying between us and the CMB in that direction. Because even after the CMB is released, the universe evolves. Light passes through changing gravitational landscapes. And there is a known effect where photons passing through large, underdense regions can end up slightly cooler due to the way expanding spacetime changes the energy of the light along the journey. So, the void idea is comforting. It stays inside known physics. It says, yes, it's weird, but it's still the same universe. And for a while, people hunted for such a void, or tried to model whether a realistic void could produce a spot that cold. But here's where the crack opens again. The void explanation, depending on the details, can struggle to fully account for the strength and shape of the cold spot, not in a clean, decisive way, more in the frustrating way that keeps the debate alive, as if the simplest story is close, but not quite snug. And when a mystery refuses to become snug, a different kind of explanation starts walking across the stage, one that feels almost too dramatic to say out loud. What if the cold spot is not just a feature inside our universe, but a bruise from contact with something beyond it? This is where the narrative turns from unusual structure into uncomfortable possibility. Because there is a class of ideas in cosmology called eternal inflation and bubble universes. The basic image is this. In some models, space-time can inflate exponentially, creating vast regions that keep inflating while pockets of space stop inflating and become something like a universe, a bubble. Our universe in that picture would be one bubble among many. Most bubbles might be lifeless. Most might have different physical constants. Most might be born and vanish without anyone to notice. But here's the dangerous thought. If multiple bubbles exist, then collisions become possible. Not common perhaps, but possible. And if a bubble collision happened in the early history of our universe, it might leave a subtle imprint, not a Hollywood explosion, not a visible crack in the sky like broken glass. Something quieter, a statistical scar in the CMB, a circularish disturbance, a region that looks a little too smooth, or a little too cold, or just a little too wrong. That's why the cold spot becomes a perfect character in this story, because it is exactly the kind of thing that bubble collision proponents point to as the kind of signature you'd go looking for. It's not proof, it's not a smoking gun, but it is the right shape of unease, a feature that could be explained by mundane structure, or could be something far stranger. And in competitor-style storytelling, you don't need to pick a final answer to make the point land. You only need to show the fork in the road. On one side, the cold spot is a void effect and statistics. On the other side, the cold spot is a leftover mark from a time when our universe wasn't alone. And when you hold both possibilities in your mind, something subtle happens. The sky stops feeling like a picture. It starts feeling like a surface that can be touched, dented, imprinted, which loops beautifully back into the earlier cracks we have already laid down. The idea that gravity might leak into hidden dimensions. The idea that large-scale motion might hint at structure beyond what we can see. The idea that our complete map is really just a local scan. All of it starts to rhyme, and the cold spot becomes less like a single anomaly and more like a symbol of how thin our confidence can be. Because the CMB is not just any data set. It's the data set we treat like a baseline reality, a cosmic calibration standard. So if that baseline contains a feature that we can't comfortably file away, it makes you wonder what else is quietly baked into the sky. Now, to keep our feet on the ground, we should say the honest thing in the calmest voice possible. Scientists argue about the significance of the cold spot. Some see it as consistent with statistical chance in a universe this large. Some see it as unusual enough to justify deeper speculation. Some focus on voids in late-time physics. Some explore bubble collision patterns in early universe models. And the reason this remains a crack is not because the cold spot proves anything. It's because it exposes how easily a single stubborn feature can reopen the biggest questions. Questions that feel almost too big for a bedtime video, and yet somehow perfect for one. Because if you're trying to fall asleep, nothing softens the mind like scale. Nothing relaxes the grip of everyday worries like remembering you live inside a mystery that doesn't shout, a mystery that whispers through a patch of sky that is slightly colder than it ought to be. And if you let the idea drift through your mind for a moment, gently, without forcing it to become certainty, you can feel the tone of it, the possibility that the universe has been touched, not in a spiritual way, in a physical cosmic way. Like two expanding regions of spacetime brushing against each other in the early dark and leaving a faint mark that, billions of years later, still shows up when we listen carefully enough. And that brings us to the next crack almost inevitably. Because once you accept that the sky can carry scars, the deepest scar question appears. Not why is there a cold spot, but what is information doing in this universe? Because if a collision is possible, if imprints can exist, if the sky keeps records, then information is not just a human concept, it's a physical thing. And there is one place in physics where information becomes so central that the entire framework starts to tremble. Black holes. Because black holes don't just bend light. They test whether the universe is allowed to forget. So as the cold spot fades into the background of the mind like a strange shadow on the oldest photograph ever taken, we turn toward the darkest objects in the cosmos and ask whether reality keeps its records perfectly, or whether somewhere in the deepest gravity wells, the universe has been quietly erasing the truth. Tonight, we reach the last crack, and it's the one that doesn't just threaten a theory, it threatens the idea that reality keeps receipts, because physics at its core is a promise. If you know what something is right now, you should be able to predict what it becomes next. Not perfectly, not in practice, but in principle. That promise has a name scientists rarely say out loud in casual conversation. Unitarity. It's the rule that says information is never truly destroyed. You can scramble it, you can hide it, you can spread it across the cosmos like ash in the wind, but you cannot erase it. And if that promise is broken, the floor under modern physics doesn't just creak, it dissolves. Because if information can vanish, then cause and effect becomes optional. Then prediction becomes superstition. Then physics becomes a story we tell ourselves because it used to work. Now here is the uncomfortable part. There is one object in the universe that seems to make information disappear on schedule, with no apology, with no visible mechanism, and with enough confidence that the math either has to bend or break. A black hole. Not the cinematic kind, not a swirling portal, not a monster with a mouth. A black hole is simpler than that. It is a region of spacetime where the concept of outside influence fails, a place where, once you cross a certain boundary, the future has only one direction. That boundary has a gentle name, the event horizon. Not a wall you hit, not a surface you can touch, just a line in spacetime where escape stops being a meaningful verb. From far away, a black hole looks almost boring, a dark sphere, a gravitational lens, a distortion. But from the inside of the equations, it behaves like a shredder for identity. Imagine you take a library, every book, every page, every margin note, every fingerprint on the cover, all the information that makes each book itself. Now imagine you feed that library into a black hole. What comes out? According to the earliest, cleanest version of the story, nothing that remembers. The black hole might radiate. It might slowly leak energy. It might evaporate over absurd stretches of time. But the radiation looks thermal, random, like the glow of a warm object. And if it's truly random, it carries no detailed imprint of what fell in. So the ending becomes unsettlingly simple. A black hole forms. Things fall in. The black hole evaporates. And when it is gone, the information is gone with it. That outcome is not just a weird curiosity. It's a direct contradiction. Because quantum mechanics, the most accurate machine humans have ever built for predicting reality, does not allow true deletion. If black holes delete information, then quantum mechanics is wrong in a fundamental way. And if quantum mechanics is wrong, then almost everything we build on top of it becomes a castle on fog. So, physicists did what they always do when a contradiction appears. They refused to let it stand. They fought for decades, not with opinions, with papers, with calculations, with arguments so sharp they became legendary. It wasn't a debate about taste. It was a debate about what the universe is allowed to do. One side said, in effect, the horizon is real and the information is gone. Another side said, no, the universe doesn't forget. The information must be encoded somehow. Then the story got stranger. Because the more carefully physicists looked at black holes, the more the black hole started to feel less like a hole, and more like a hard drive, not in the sci-fi sense, in a precise mathematical sense. Here is the first pivot. If you ask, how much information can you store inside a region of space? Your intuition says, it should scale with volume. A bigger room stores more stuff, more shelves, more boxes, more memory. Volume. But black holes whisper a different rule. The maximum information you can pack into a region seems to scale with the area of its boundary. Area, not volume. That is an upside-down result. It's like discovering that the storage capacity of your laptop depends on the surface of the screen, not the space inside the casing. This idea hardened into something called the holographic principle. The name sounds poetic, but the claim is blunt. Everything that happens in a volume of space might be fully described by information written on the boundary of that space, as if the three-dimensional world is a projection, a rendering, a display, like a hologram. If you've ever looked at a holographic sticker, you know the trick. A flat surface can contain a full 3D image, depending on how the information is encoded and how you view it. The holographic principle takes that vibe and turns it into physics. And suddenly, black holes are not information erasers. They are information compressors. They take whatever falls in and smear its description onto the horizon. Not as a neat label you can read, not as a list, not as a file folder, but as an unimaginably complex pattern. A pattern so fine-grained that to recover the original would require controlling the entire horizon like an instrument, which, in practice, you cannot do. But in principle, the information is still there. Not destroyed, just scrambled beyond recognition. This is the point where the metaphor shifts. Because the horizon stops being the edge of the hole, it becomes a surface where reality does accounting, a place where the universe keeps the books. Now we reach the second pivot, and this one feels like a magic trick that accidentally became true. Physicists discovered a situation where gravity in one space can be mathematically equivalent to a quantum theory, with no gravity living on the boundary of that space. A kind of translation dictionary, a way to say the same sentence in two different languages of reality. This relationship is famous in a certain corner of physics. It's often discussed using the phrase ADS/CFT. You don't need the full acronym tonight. You don't need the full geometry. What matters is the vibe of what it implies. It implies that a world with gravity can be fully described by a world without gravity, living on the edge. That's not a metaphor. That's not a guess. That's a mathematical equivalence in special settings. And once you accept that such a dictionary can exist, it does something to your sense of solidity. Because now depth can be emergent. Now the inside can be a consequence of information and processing on the outside. Now space itself starts to feel like a product, not a stage. A product. At this point, a calm fear enters the room. If space can be emergent, then it might not be continuous. It might have a smallest meaningful unit. Not just smallest measurable with our current tools, smallest meaningful period. A pixel size for reality. And that brings us to the Planck scale. The Planck length is often described as an extremely tiny distance where our usual ideas about space-time stop behaving nicely. It's not necessarily a literal minimum length in the way a Lego brick has a minimum size, but it is a signpost, a warning label. It says, somewhere around here, our smooth picture becomes suspicious. And when you pair that with the holographic principle, you get a very specific mood. A mood that says the universe may have an information budget. Not infinite, not arbitrarily dense. A budget. And if there is a budget, then the universe is not an endlessly divisible continuum. It is constrained, quantized in some deep informational sense. So, black holes, once feared as cosmic trash cans, start to look like the cleanest place to learn the rules of storage. They are the harsh auditors of physics. They force you to ask, how much can reality remember? Now, the third pivot. And this is the one that feels almost too elegant to be safe. What is the strongest kind of connection quantum mechanics allows? Entanglement, a linkage between systems so deep that describing one without referencing the other becomes incomplete. Not a signal, not a message, not a classical tether, a shared description. For years, entanglement was treated as weird. Then it became normal. Then it became useful. Then it became inevitable. And then, in a twist that sounds like a dare, some physicists began to suspect something radical. Maybe entanglement isn't just something that happens inside space-time. Maybe entanglement helps create space-time. This is where the phrase ER equals EPR enters the story. Again, you don't need the full historical naming tonight. You just need the shape of the idea. ER points to wormholes and general relativity, the notion of a bridge connecting regions of space-time. EPR points to entanglement, the quantum linkage that Einstein once disliked. The proposal suggests that these may be two faces of the same deeper structure, that a wormhole-like connection and an entangled connection might be related under the hood. Not necessarily a traversable portal, not a shortcut you can fly through, but a geometric expression of quantum connectivity. If that is even partly true, it changes the hierarchy. Space becomes the secondary thing. Entanglement becomes the primary thing. Distance becomes a symptom. Geometry becomes an effect. And the black hole information paradox stops being a niche physics headache. It becomes a flashlight shining on the construction scaffolding of reality. Because now the question is not just, where did the information go? It becomes, what is space made of if information can't leave the ledger? And here is where the mood turns quietly terrifying. If space-time is woven from entanglement, then the stability of the world depends on the stability of those patterns. Not stable in the emotional sense, stable in the structural sense. The way a bridge depends on tension. So, when you hear, if you pull the wrong thread, it isn't poetic. It's a technical intuition dressed in human language. Because a thread might not break a wall. It might redefine what wall means. It might not collapse a building. It might collapse the concept of separation. And that is why this final crack is so important. The earlier cracks sounded like discrepancies, anomalies, weird numbers. This one is different. This one forces a yes or no answer. Either the universe deletes information, or reality is far more encoded than our senses admit. Either physics breaks at the horizon, or the horizon is a surface of bookkeeping, and the world we experience is a projection of deeper accounting. Either space is fundamental, or space is something stitched together by relationships. And if that last option is even partly true, then it means something profound. You are not resting inside a static stage. You are resting inside a structure that is continuously maintained by consistent rules. Rules that do not need your awareness to operate. Rules that hold even when you sleep. Rules that hold even when you look away. In a strange way, it's comforting. Because the universe, for all its mystery, is not careless. It doesn't throw information away lightly. It hides it. It encrypts it. It distributes it. But it keeps it. And that means the world is not random in the way nightmares are random. It is deep, sometimes too deep for comfort, but deep in a way that suggests coherence, not chaos. So as we step away from this last crack, let me leave you with a gentle question to carry into the dark. If the universe is stitched together by invisible relationships, what else in your life is held up by threads you never see? If you'd like, tell me in a comment which crack felt most real to you tonight. Just a few words, where you're listening from, and which idea lingered. And if these slow, strange journeys help you sleep, you can like the video and subscribe to the Quantum Slumber. It helps this quiet corner find the people who need it. But for now, you don't have to solve anything. You can let the paradox sit on the shelf. Let the equations keep their secrets. Let the universe do its quiet accounting without your help. All you need to do is rest. Let your thoughts loosen their grip. Let the day fall away. And if your mind drifts back to that final image, remember it gently. Not a wall collapsing, not a universe breaking, just a fabric of connections holding. Good night.